Good evening, everyone. Welcome to this live session related to the content of week 2 of this NPTEL course on hydraulic engineering. And today we shall be discussing problem related to fluid kinematics, which will involve continuity equation, then some portion of Bernoulli's equation as well, and then potential function and stream function. To begin with, we will discuss some fundamental concepts related to this week's content. So let's start. Say there is a fluid element. Say there is a infinitesimal fluid element. So this is the fluid element. Say this is our Cartesian coordinate system. Say this is our x direction. Then say this is our y direction, and this is our z direction. Now with this, for this fluid element, if we consider the mass flow rate along x, y, and z direction, that is mass flux rho u along x direction, rho v along y direction, and rho w along z direction, then the general continuity equation in Cartesian coordinate system will be del rho by del t plus del rho u del x plus del rho v del y plus del rho w by del z is equal to 0. Now this is the general continuity equation. Now uh, the most of the flows that you encounter from the civil engineering point of view are incompressible flow, because we are mainly concerned with the flow of water. So for incompressible flow, density is a constant. Now for a constant density, if we consider that the rho is constant, then this first term becomes 0, and all this rho being constant will come out of the differentiation, and the final equation that will get for that is the continuity equation for incompressible fluid will become del u by del x plus del v by del y plus del w by del z is equal to 0. So this is the continuity equation for a incompressible fluid. Now any given velocity field, say we have a velocity field v, which is basically having three components, capital V, u, v, and w. U along x-axis, v along y-axis, and w along z-axis, represented by I cap, z cap, and k cap, that is a unit vectors along x-axis, y-axis, and z-axis, such that u is a function of space, that is three-dimensional space and time in general. V is a function of space and time. Similarly, w is a function of space and time. Then if this velocity field satisfies this equation, that is, in terms of vector equation, the divergence of this velocity field is equal to 0, then it means that the velocity field V given by u I cap plus v j cap plus w k cap, means this equation here, if it satisfies this, that is the divergence of this velocity field is 0, then it means that the flow is incompressible and it represents a possible case of incompressible fluid flow. It represents a possible case of incompressible fluid flow. Now this equation, this general equation can be written in different forms. For example, in vector form, if you write this equation in vector form, what you can write? You can write that del rho del t plus, if we look at these three terms carefully, that is from here to here, this can be written as del dot rho v equal to 0. So this is one form. Okay, so this is the Cartesian form. In vector form it can be written like this. Okay, another form in which you can write this equation is, now the general equation is del rho by del t plus del rho u del x plus del rho v del y plus del rho w del z is equal to 0. So this equation can be written as del rho by del t plus u del rho del x plus rho del u del x plus v del rho del y plus rho del v del y plus w del rho del z plus rho del w del z is equal to 0, or del rho del t. Now if we club together these terms u, v and w, then clubbing these terms together, we can write this as u del rho del x plus v del rho del y plus w del rho del z plus rho del u del x plus del v del y plus del w del z is equal to 0. Now if we look carefully, then these terms, these three terms can be written as v dot del rho. Okay, v dot del rho and these three terms can be written as rho del dot v. Okay, so if you write finally, what we can write? We can write this equation like this also: del rho del t plus v dot del rho plus rho del dot v is equal to 0. Okay, now if it is a incompressible flow, from here also we can get, then this particular term del rho means this entire term, the second term will be 0, this will be 0, rho is constant, so finally we are left with del dot v equal to 0. So whether you go with a vector sense or you go with a Cartesian coordinate sense, for incompressible fluid flow the continuity equation is the divergence of velocity is equal to 0. Now this divergence of velocity has one more meaning. Okay, in general this divergence of velocity, that is del u by del x plus del v by del y plus del w by del z is equal to d dt of del v by v. That is, the time rate of volumetric strain is also represented by this, but this is valid for any general fluid flow case. However, for incompressible flow the entire continuity equation reduces to this. Okay, now after this, the second concept that is of utmost importance for today's live session is the concept of a stream function and the concept of a potential function. Okay, so what is a stream function and what is a potential function? So first of all, let us say what is a potential function. Now a potential function phi is a scalar function. Okay, it is a scalar function such that u is equal to del phi by del x, v is equal to del phi by del y, and w is equal to del phi by del z. Now what are these u, v and w? U, v and w are the x component of velocity, y component of velocity and the z component of velocity respectively. So what is a potential function? Potential function is represented generally by symbol phi. It is a scalar function of space and time such that the x component of velocity is given by the partial derivative of phi with respect to the x, y component of velocity is given by the partial derivative of phi with respect to y, and the z component of velocity w is given by the partial derivative of phi with respect to z. Okay, so these are the three components of velocity that we have seen. Now if phi exists, okay, if phi exists, then we can directly say that the flow is irrotational. Okay, if phi exists, then we can directly comment, we can directly say, you can directly deduce that the flow is irrotational. How? We'll come back to stream function after we have after we decide phi. Okay, how? Let us see how we can say that. So for irrotational flow, let us consider a two-dimensional flow. So for a two-dimensional flow, v is equal to u I cap plus say v j cap. There won't be any z component w because we have considered, we have assumed that the flow is, two-dimensional. So for a two-dimensional flow, v is equal to u I cap, means the total velocity field is equal to u I cap and v j cap, such that this u is a function of space and time. Similarly, v is a function of three-dimensional space and time. Okay, now rotation omega z for such a flow is given by half of if we allow the cyclic rule, then z x y del v del x minus del u del y. So this is the rotation. Now if this we say that the flow is irrotational, if this omega z is equal to 0, we say that the flow is irrotational. Okay, now from the definition of potential function, we have u is equal to del phi by del x and v is equal to del phi by del y. So in that case, what will be del v by del x? That is the first term. Del v by del x will be del x of, okay, it will be del x of v. So v is del phi by del y. So del 2 phi by del x del y. And similarly, what will be del u by del y? That is the second term here. Del u by del y will be equal to del y of, what is u? U is del phi by del x. So this will be del 2 phi del y del x. Now since phi is a continuous function of space and time, then it means that del 2 phi del x del y is equal to del 2 phi del y del x, and if these are equal, then this is equal to 0. Okay, so simply if phi exists for a flow case, then we have seen that the rotational component is equal to 0, and that's why, what is the conclusion? The conclusion is, if phi exists, if for a flow situation, if phi exists, then the flow is irrotational. Apart from this, if it satisfies Laplace equation, now what is Laplace equation? Laplace equation is del 2 phi by del x square plus del 2 phi in 2D, suppose if you write, is equal to 0, or in vector notation we can write this as del 2 phi equal to 0, where del 2 is the Laplacian operator. Okay, del 2 is the Laplacian operator. So Laplacian operator. Now if it satisfies Laplace equation, then what happens? Okay, so first of all, let us examine the situation when the potential function phi satisfies Laplace equation. Okay, so we have already seen, so one thing is for sure, that since if phi exists, then the flow is irrotational. Now we are examining the fact that if phi satisfies Laplace equation, let us write the two-dimensional equation for steady incompressible fluid flow. So it is del u del x plus del v del y is equal to 0. Del x, what is u in terms of phi? It will be del phi by del x, plus del y, what is v in terms of phi? It is del phi by del y. So these two are equal to 0. Now this amounts to del 2 phi by del x square plus del 2 phi by del y square is equal to 0. Now this is what? This is the Laplace equation. So if phi exists, flow is irrotational. And other than that, in addition to that, if it satisfies Laplace equation, then the flow is steady, incompressible, because the only possibility by which this potential function phi can satisfy Laplace equation is when the flow is steady and incompressible. So, and irrotationality is definitely there, irrotational flow, because phi, the existence of phi itself confirms the irrotationality condition. So what is important that you need to remember, which is very important even for competitive exams, if phi exists, then the flow is irrotational. And in addition to that, if it satisfies Laplace equation, then the flow is steady, incompressible, irrotational flow. So this is all for your potential function. Next, one more important function that we have seen is important is the stream function. Okay, one more important function is the stream function. Stream function in general is denoted by psi. Okay, now how this is defined? U is equal to del psi by del y, and v is equal to minus of del psi by del x. Okay, so what is a stream function psi? Stream function psi is a scalar function of space and time such that the x component of velocity is given by the partial derivative of psi with respect to the y direction, and the y directional velocity v is given by the negative of the partial derivative of psi with respect to the x direction. Okay, so this u is equal to del phi by del x, and this v is equal to del phi by del y. Okay, so this itself gives us the relationship between psi and phi. Now let us see, as we have seen in the case of potential function phi, if phi exists, if potential function exists, then the flow is irrotational, and if it satisfies Laplace equation, then it is also a case of steady incompressible flow. It means that if phi satisfies Laplace equation, then the flow is steady, incompressible and irrotational. Okay. Similarly, what if psi exists? If psi exists, then the flow may be rotational or irrotational. Okay. But in addition to that, if it satisfies Laplace equation, then let us see what happens. See, omega z is equal to, that is the rotational for 2D case, is given by del v by del x minus of, sorry, omega z is equal to half of del v by del x minus of del u by del y. Okay, now what is v in terms of psi? V can be written as del x of minus of del psi by del x minus of del y of u is what? Del psi by del y. So this is effectively omega z is equal to half of minus del 2 psi del x square plus del 2 psi del y square. Okay, now if the flow is irrotational, then this omega z term will be equal to 0. So from this equation, what will you get? Del 2 psi by del x square plus del 2 psi by del y square is equal to 0. Or this is what? This is the Laplace equation in terms of the stream function psi. So how we have obtained this Laplace equation for stream function psi? When we have assumed that this omega z, that is the rotational component, is equal to 0. It means that it represents irrotationally condition. So this is again a very important condition. Merely the existence of psi does not tell us anything about whether the flow is rotational or irrotational. However, if psi satisfies Laplace equation, then we can say with certainty that the flow is irrotational. Okay, then we can say with certainty that the flow is irrotational. So this is all about phi and psi. The next important thing that we have seen in this particular week's lecture is about Bernoulli's equation. Okay, is about Bernoulli's equation. Now, during the last live lecture, we have already seen and we have already discussed that in any problem of mechanics, it may be solid mechanics, it may be fluid mechanics, it may be soil mechanics, in any mechanics, in any continuum mechanics problem, in order to analyze a situation, okay, the utmost importance is given to the conservation laws. Okay, the law of conservation of mass, the law of conservation of linear momentum, the law of conservation of angular momentum, and the law of conservation of energy in a Newtonian framework. Now, in case of fluid, we have already seen the mass conservation equation, which is the continuity equation. The linear conservation of linear momentum is basically represented by the Navier-Stokes equation. And then we have the conservation of energy as well. The conservation of energy under certain strict assumption is given by Bernoulli's equation. Now Bernoulli's equation, what is the statement? Suppose the fluid is flowing between 2 points, say from point 1 to point 2, then according to Bernoulli's equation, if this fluid is an ideal fluid, then P1 by rho g plus V1 square by twice g plus Z1 is equal to P2 by rho g plus V2 square by twice g plus Z2. It means that a different section, the sum of these three terms are a constant. Okay. But what exactly is the significance of these three terms? Let us look at this term P1 by rho g. P1 by rho g is nothing but pressure energy per unit weight. Okay. Similarly, second term V1 square by twice g, where V is the average velocity at that section, V1 square by twice g is the kinetic energy per unit weight. Okay, so the second term is the kinetic energy per unit weight, and the third term is nothing but the potential energy per unit weight with respect to a reference datum or benchmark. Okay, now see what is pressure. The hydrostatic pressure is given by rho g h. Okay, force is pressure into area. Okay, now energy, pressure energy will be pressure into area. Okay, multiplied with certain displacement, say I am writing d. Okay, now divided by, because it is pressure energy per unit weight. Okay, so weight is given by m into g. Okay, now what is m? M is mass. Mass can be written as density into volume. So this can be written as P A D divided by rho V G. Now area into some displacement is again the volume. So this and this cancel out and we are left with P by rho G. So that's how we are getting pressure energy per unit weight. Similarly, kinetic energy is given by half of mv square. Per unit weight is divided by mg. So mm cancel out. It is v square by twice g. That is the second term. And the potential energy is given by mzz. Per unit weight is divided by mg. So we are effectively left with only z. So this is the third term. So basically, the first term is the pressure energy per unit weight, the second energy is the kinetic energy per unit weight, and the third part is the potential energy per unit weight. So Bernoulli's equation tells us that for an ideal fluid, the summation of these three energies per unit weight. Okay, now when you convert these things into per unit weight, the unit becomes meter. Okay, the unit becomes meter, or it becomes the dimension of this particular thing become L, where L represents length. Okay. However, this physically does not signify any length. It signifies energy per unit weight. Again, this is a very important question for competitive exams. Okay, they may give you that what does this thing represent. Now, simply by looking at the unit, you can give the answer as length, but mind it, it does not represent length. It represents energy per unit weight, whose unit is same as the unit of length. That is the only similarity. Otherwise, it does not signify length. Then, this is for an ideal fluid. Now, what is the ideal fluid? An ideal fluid is a fluid whose viscosity, what is the ideal fluid? Whose viscosity is equal to 0. Okay. But what if it is a real fluid? In case of a real fluid, what will be Bernoulli's equation? In case of real fluid, the Bernoulli's equation can be written as P1 by rho g plus V1 square by twice g plus Z1 is equal to P2 by rho g plus V2 square by twice g plus Z2. In addition to that, there is a term HL which signifies head loss. Now head loss, what is head loss? Whenever flow is taking place between two sections, say from section 1 to section 2, in between there is some loss of energy. Okay, majorly because of the friction between the fluid and the wall of the pipe or maybe the channels. Then there are some also minor losses which you will go through as you advance with this particular course. You will read about, you will go through the different types of minor losses, but at this point it is very important to know that there are some losses. Okay, so out of these losses, there is a major component, there are some minor components. The major component is because of friction and the minor component is because of different reasons. Okay, I'm not naming those things. When we will go through the content of that particular week in pipe flow, we'll discuss those as well. Okay, so for a real fluid, this is the Bernoulli's equation for a real fluid. So that is all about Bernoulli's equation. Okay, one more important thing about stream function and potential function. Okay, you may get some question that prove that equipotential lines, okay, you have to prove that equipotential lines and streamlines are perpendicular to each other. Okay, so for that you basically need the idea of potential functions and stream functions. Okay, now what are equipotential line? A equipotential line is a line such that as you move along the line the value of phi is constant, and streamline is a line such that along that line the value of psi is constant. Okay, now flow always takes place from higher potential to lower potential because flow always takes, so this is say phi 1, so this is our equipotential line such that along this line the value of the potential function is phi 1, along this line say it is phi 2, phi 3, phi 4 and so on, and say this is our streamlines. Okay, streamlines, say along this it is psi 1, this is psi 2, this is psi 3. So these points of intersection are always 90 degree, they cut each other at 90 degree always. Okay, now if we say that phi 1 is greater than phi 2 is greater than phi 3 and so on, then this is the flow direction. Okay, because it always takes place from higher potential to lower potential. Okay, always remember that flow always takes place from higher energy to lower energy. To give you an example, consider that there is a hill. Okay, now if you have to supply, say on the top of the hill there is a reservoir. Okay, there is a reservoir and you need to supply water from this reservoir to a village which say lies here at the bottom of the hill. Then you can do it very easily. You just lay a pipeline or maybe a canal, and this directly under the action of gravity water will move from this reservoir to the village. Okay, but suppose you consider a reverse situation. Suppose this is the hill, your village lies on the top of the hill and the reservoir is at a lower elevation. Now you need to supply water, so you cannot directly do this because it is against the gravity. Okay, so we have already seen that the total energy is having three components. Okay, sorry, the total energy is having three components: the pressure energy per unit weight, the kinetic energy per unit weight, and the potential energy per unit weight. Okay, now on the top of that hill the potential energy is high in comparison to the bottom of the hill. So if you want to transfer water from the bottom to the top, then you need to do something which will increase the total energy of water here. So what we can do, we can make use of a pump. Now if you make use of a pump, what does this pump do? This pump increase the pressure head, okay, the pressure energy, okay. It enhances the pressure energy, and as a result of which the total energy at that location increases, okay. And as the total energy increases, the water is supplied from this point to this point, okay. See, the total potential energy at this point is less, but by employing a pump, you are increasing the pressure energy, and as a result, the total energy at this point is increased, and then you are supplying. Okay. So, water always flows from a region of higher energy to lower energy. Okay. So, what we're discussing? We're discussing about that the potential line are lines along which the value of phi is constant. Equipotential lines and streamlines are lines along which the value of psi is constant, and whenever they cut each other at 90 degree. They are always orthogonal to each other. So how you can prove that? Okay, so in order to prove that, let us consider a potential function phi, which is a function of space, say two-dimensional space, x and y. So the total derivative d phi will be equal to del phi by del x dx plus del phi by del y dy. Okay. Now, what is del phi by del x? It is u dx. What is del phi by del y? It is v dy. Okay. So, d phi is equal to u dx plus v dy. Now, since along a equipotential line, the value of phi is a constant. So, what will be the value of d phi? The value of d phi will be 0. So, for a equipotential line, u dx plus v dy is equal to 0, or from here what we can get? We get that dy by dx is equal to minus of u v dy dx, yeah. So minus of u by v, okay. So from equipotential lines you are getting the slope of a equipotential line is given by minus u by v. Next you consider a streamline, okay. Next you consider a streamline. So again streamline psi, which is a function of x and y. Okay, then the total derivative d psi is given by del psi by del x plus dx plus del psi by del y dy. Okay, so what is del psi by del x? What is the definition of psi we have seen? The definition of psi that we have seen, yeah, u is equal to del psi by del y, v is equal to minus of del psi by del x. Okay, so if we use this, del psi by del x can be written as minus of v dx, and del psi by del y is u dy. Okay, again along a stream function the value of psi is along a streamline the value of psi is a constant, therefore d psi will be equal to 0, and from this what you are getting, u dy is equal to v dx, or dy by dx is equal to v by u. So the slopes of a streamline is given by v by u. Now from geometry we know that if two lines are perpendicular to each other, then say there are two lines, line 1 and line 2, which are perpendicular to each other, then the product of their slopes, that is if m1 is the slope of line 1 and m2 is the slope of line 2, then the product of their slope is equal to minus 1. So the slope of the streamline is v by u, and slope of the potential equipotential line is minus of u by v. So if you multiply these two, minus of u by v, what you are getting? You are getting minus 1. So hence it is proved that equipotential lines and streamlines are perpendicular or orthogonal to each other. Okay, so this is again a very important concept which you should remember. And one last concept before we move to the problems is that if you consider two streamlines, psi 1 and psi 2, then the difference between these two delta psi is equal to the discharge that is taking place between these two streamlines. So dq, okay, so dq is equal to delta psi. The difference in the discharge is given by this dq. So I hope it is clear till now. Is it clear? So we have seen what exactly are the different forms of continuity equation in Cartesian coordinate form, then in vector form how you can write it, then what is the significance of divergence of velocity. uh, Divergence of velocity in general represents the time rate of change of the volumetric strain. However, for an incompressible fluid flow, it also represents the conservation of mass or the continuity equation. Then we have seen the various the definition and the various properties associated with the potential function phi and stream function psi. Then we have seen some very important properties of equipotential lines and streamlines. Then we have seen some aspects of Bernoulli's equation. Okay, so with this, we'll move to the problems for today's session. But before that, do you have any question? I think Kalai Selvan has just joined, so you might not be having any clue what we're discussing. But Sonam Kumari, do you have any doubt? You can write in the chat box also in the messages. Okay. So if there are no doubts, I suppose that there are no doubts. So if there are no doubts, then let's move to the problems. Okay. So the first problem, determine whether the continuity equation. Okay. Just 1 second. Huh. Okay. So this is the first question. If to determine whether the continuity equation is satisfied by the velocity components, so three velocity components are given to you: u x square y, v twice xy minus xy square, and w x square minus z square. So for this u, v, and w, you need to check whether it satisfies continuity equation or not for an incompressible fluid. Okay. So please try this problem. Try this problem for some time, then we will discuss the solution also, don't worry. So have you done this? Okay, let's look at the solution. Okay, so we have already seen the continuity equation. The general continuity equation is del rho by del t plus del rho u del x plus del rho v del y plus del rho w del z is equal to 0. Okay, now if the this can be written in different ways. This can be written in different ways. So how this thing can be written? You can, in vector form, you can write this equation as del rho by del t plus del dot rho v is equal to 0. Okay, one more way, if you break down this, you can write this as del rho by del t plus rho del dot v plus v dot del rho equal to 0. Okay, but all these three forms are one and the same. Okay, all these three forms are nothing but one and the same. Okay, same, which represent the general continuity equation for fluid flow. However, for this problem you have to check whether these velocity components satisfy the continuity equation for incompressible flow. Okay, so for incompressible flow, what what is the condition? Rho is a constant. Okay, rho is a constant. Now if rho is a constant, this term becomes 0, all this rho will come out of the differentiation, and effectively you will be left with del u by del x plus del v by del y plus del w by del z equal to 0. So this is nothing but, in vector notation, del dot v is equal to 0, that is the divergence of velocity equal to 0. Now divergence of velocity has, for general fluid flow case, has a different meaning. Divergence of velocity is representative of the time rate of change of the volumetric strain. So what you can conclude? You can conclude that for an incompressible fluid, the time rate of change of volumetric strain is 0. Okay, or the volumetric strain rate, the volumetric strain rate, okay, is what? If the time rate of change of the volumetric strain, okay, the total volumetric strain is 0, it means that it is a constant, and that is the meaning of significance of incompressibility. Anyways, so for this problem you need to check this condition. So for the given problem, u is equal to x square y v is equal to twice xy minus xy square, and w is equal to x square minus z square. Okay, So what will be del u by del x? Del u by del x will be twice xy. What will be del v by del y? Del v by del y will be twice x minus twice xy. And what will be del w by del z? Del w by del z will be minus of twice z. Now if you add these three, this, this and this, are you getting 0? Are this the summation of these three terms? Is it equal to 0? No, right? It is not equal to 0. It is not equal to 0. Hence, because what will you get? You will effectively be left with this term and this term will cancel out. So twice of x minus z will be there, which is not equal to 0 for any x and z. Okay. So that's why this does not represent any possible case of fluid continuity equation for an incompressible fluid. Is it clear? Is it clear, this problem? Okay. So if there are no questions, I suppose that everything is clear. Then let's move to the next problem. So this is the next problem. The diameter of a tapering pipe at sections 1, 1 and 2, 2 are 100 millimeter and 150 millimeter respectively. If the velocity of water flowing through the pipe at section 1, 1 is 5 meter per second, find the discharge through the pipe and the velocity of water at section 2, 2. Okay. So what is the situation? Let me explain you the situation. There is a tapering pipe. Okay. And in that pipe, two sections were considered. Okay. This is section 1, 1 and then this is section 2, 2. Such that the diameter of the pipe at section 1, it is a circular pipe with the variable diameter. The diameter here is 100 millimeter and the diameter here is 150 millimeter. Apart from that, what is given to you at section 1, 1? Okay, at section 1, 1, the velocity is 5 meter per second. Okay, so you need to find what is the discharge q through this pipe and you need to find the value of v2, the velocity at section 2. So please try this problem. I'm giving you 6-7 minutes. You try these problems and then we'll look at the solution. Once you calculate, you can write the answer. You can either tell your answer or you can write in the messages, the in call messages. Okay. Any answers? This is a very simple problem. You need to directly apply Bernoulli's equation. And the flowing fluid is water. And it is a horizontal pipe. Okay, because nothing has been mentioned about the inclination or the slope. So you consider this as a horizontal pipe. So it is a very simple problem. And for the first part, it is the discharge. You don't need Bernoulli's equation also, because at section 1:1 the velocity is given, the diameter is given to you. So you multiply area, you calculate the diameter, area from the diameter, and you multiply this area with velocity, that will give you the discharge. Okay, and by continuity this discharge will be same as the discharge at the other end. You need to apply, or even if you don't apply Bernoulli's equation, then also it is fine. You can directly calculate it from continuity equation. A1 V1 equal to A2 V2. Okay, that will be the easiest. A1 V1 equal to A2 V2. A1 and V1 are known, A2 is known, you need to compute V2. Okay, let us look at the solution. So, what will be A1? A1 will be pi d1 square by 4. So, pi, what is d1? 100 millimeter. So, converted to meter, it will be 100 into 10 to the power minus 3 whole square divided by 4. So, this is, let me check, pi into 100 into 10 to the power minus 3 whole square divided by 4. So this is approximately coming out to be 7.854 into 10 to the power minus 3 meter square. Okay, and V1 is 5 meters second. What is A2? A2 will be pi d2 square by 4. So pi into d2 is 150 into 10 to the power minus 3 whole square divided by 4. So this is approximately pi into 150 into 10 to the power minus 3 whole square 0.0177 meter square. Okay, let me recheck the calculation for A1. Yeah, this is fine. And for A2, yeah, it is fine. So now if we apply continuity equation, then what we have? We have A1 V1 is equal to A2 V2. So A1 is 7.854 into 10 to the power minus 3 into 5 is equal to 0.0177 into V2. So from here V2 will be equal to 7.854 into 10 to the power minus 3 into 5 divided by 0.0177, 2.22. Okay, so it is approximately 2.22 meter per second. So this is a simple application of continuity equation, a1 v1 equal to a2 v2. So I hope this problem is clear. Somebody? Yeah. Is the screen visible? But I have shared the screen. Is it yet not visible? Yeah, yeah, yeah. Please do so. Fine. Is it visible now, screen? I don't know because I have shared my screen. There, just let me stop presenting and then I'll again share. Yeah, I have shared once again. Is it visible? I don't know. See, anyways, let me proceed with the session because I have shared my screen. Maybe there is some issue at your end, uh, or you can like you can once exit and then you can join again. Otherwise, this session recordings will be available. Okay. So let me proceed with the problem. So let's move to the next problem. There is a pipe which is 300-meter long and it is laid at a slope of 1 in 100. That is, if it moves 100 units in the horizontal direction, then it moves in the vertical direction by 1 unit. And it is having a tapering diameter such that at the higher end, the diameter is 1 meter and at the lower end, the diameter is 0.5 meter. The quantity of water, that is the discharge flowing through the pipe, is 90 liters per second. If the pressure at the higher end is 70 kilonewton per meter square, you have to find the pressure at the lower end. So this particular problem is a direct application of Bernoulli's equation. So please try for some time. So for any problem, the best way is to draw the problem figure. So for this problem, there is a pipe. Sorry, this is pipe which is tapering. Sorry, a tapering pipe. Okay. Now for a tapering pipe, the slope is given. So for this particular pipe, say this is the pipe. Okay. If you consider that the center line of the slope is the datum, then it will be easier for you. Okay. And then you simply need to apply Bernoulli's equation. That is P1 by rho g plus V1 square by twice g plus Z1 is equal to P2 by rho g plus V2 square by twice g plus Z2. Now rho you can take this as 1000 kg per meter cube because the flowing fluid is water. Okay, the flowing fluid is water. The discharge in the pipe is given. You need to convert this into meter cube per second. Okay, it is given in liters per second. So please try this problem. The total length of the pipe is 300 meter. Okay, so if the total length of the pipe is 300 meter, and if you measure the center line, because the center line and the pipe walls, they will be parallel in on this particular plane. Okay, so for a 300 meter, if it moves a 100-meter unit, it will move in the vertically by 1 unit. Okay, so if it moves by 300 meters, it will be by 3 meters. So it means that the difference between Z1 and Z2, that is delta Z, is having a magnitude of 3 meter. Okay, so this is the modulus sign. Okay, it is not 131, it is a modulus sign, so it is a magnitude, it is having a magnitude of 3 meter. Then what else is given to you? The discharge is given to you. Since the diameter is at the both ends are known to you, the discharge is given to you. You can very easily calculate V1 and V2. How? V1 is equal to Q by A1 and V2 is equal to Q by A2, where A1 is equal to pi D1 square by 4 and A2 is equal to pi D2 square by 4. The value of D1 and D2 is given to you. Okay. The pressure at higher end is given to you, which is 70 kilonewton per meter square, or 70 into 10 to the power 3 Newton per meter square or Pascal. Okay. So you simply put in Bernoulli's equation and you will get the answer. Has anybody found the answer yet? let us see. P1 by rho g plus V1 square by twice g plus Z1 is equal to P2 by rho g plus V2 square by twice g plus Z2. Okay. Say 1 denotes the higher end and 2 denotes the lower end. Okay. So if 1 denotes the higher end, then this thing can be written as P1 by rho g plus V1 square by twice g plus Z1 minus Z2 is equal to P2 by rho g plus V2 square by twice g. Now the pressure is given, but at which end? Higher end it is given. So in terms of its value, 70 into 10 to the power 3 divided by 1000. Let's take G as 9.81 plus V1. What will be V1? V1 will be Q. Okay, what is Q? Q is 90 liters. So liters into 10 to the power minus 3 meter cube per second. Okay, Q divided by A1. A1 is pi into. So at the higher end, what is the diameter? 1 meter. Pi d square by 4. So this total is V1 square divided by 2 into 9.81 plus Z1 minus Z2 is 3. P2 is what is you need to calculate, divided by 1000 into 9.81 plus V2. V2 will be 90 into 10 to the power minus 3 divided by pi into 0.5 square by 4 whole square of this entire quantity divided by 2 into 9.81, because it is, yeah, 0.5 meter at the lower end. Okay, so now you see, in this entire equation, okay, in this entire equation, the only unknown is P2. So you just put the you do the calculations and you obtain the value of P2 in Newton per meter square or Pascal. So that is what you need to calculate. So is this problem clear, or you have any doubt? It's a very simple problem, but again very important, because in competitive exams like GATE you get variety of questions. Okay, very simple problems but different questions on Bernoulli's equation. So you need to do a lot of practice on this topic, Bernoulli's equation, continuities equation. Then there are few problems which involve uh, application of both Bernoulli's equation as well as continuity equation. So you need to practice a lot of questions. Okay, if there is no issue, then we can move to the next problem. So the next problem, the velocity potential function phi is given, which is minus xy cube by 3 minus x square plus x cube y by 3 plus y square. Determine the velocity components in x and y directions and show that phi represents a possible case of flow. Okay, you have to show that this phi represents a possible case of flow. Now let us discuss what we have already discussed in today's uh, session. Before doing this problem, what is phi? Okay, so what are the theories that we have discussed with respect to this phi? Let us discuss that once again. So phi, what is phi? Phi is potential function. Okay, so what is phi? Phi is potential function. What is the definition of phi? It is a scalar function of space such that the x dimensional velocity, the x component of velocity is given by del phi by del x, and the y component of velocity is given by del phi by del y. Okay, this is the second most important point. First of all, phi is known as potential function. What is its definition? Its definition, it is a scalar function such that when you find the derivative of phi, partial derivative of phi with respect to x, it gives you the x component of velocity. When you find the derivative of phi with respect to y, it gives you the y component of velocity. This is the important property. Second property is, if phi exists, okay, if phi exists, then the flow is irrotational. Why this flow is irrotational? Because if you consider a two-dimensional flow, then omega z is given by half of del v by del x minus del u by del y. Okay, in this particular definition of omega z, if you substitute the value of v and u as del phi by del y and del phi by del x, you will be getting a value of 0. So if omega z is 0, then the flow is irrotational. So it means that if phi exists, then it is sure that the flow is irrotational. Apart from that, if it satisfies Laplace equation, if phi satisfies Laplace equation, that is del 2 phi by del x square plus del 2 phi by del y square equal to 0, then it is definitely irrotational. Apart from that, it is also steady and incompressible. Okay, steady and incompressible. And along a equipotential line, phi remains constant. Okay, and for such lines, the slope of a equipotential line is given by, okay, first of all, the total derivative d phi is given by u dx plus v dy, and for equipotential line d phi is equal to 0, so dy by dx is equal to minus of u by v. This is the slope of a equipotential line. So these are the properties which we have already seen during the beginning of today's session. Okay, now let us move to the problem. If phi is given to you, what is that phi? The value of phi that is given to you is phi is equal to xy cube by 3 then minus x square plus x cube y by 3 plus y square. Okay, now you have to determine the velocity components along x and y direction. So for x direction, u is equal to del phi by del x and v is equal to del phi by del y. Okay, then for this u and v, you check the continuity equation, that is whether the divergence of v is equal to 0 or not. Okay, if it is 0, then it represents a possible case of flow. If it doesn't, then it does not represent a possible case of flow. Okay, so please try this problem. Maybe you can take 5-6 minutes and then we'll discuss the answer. So this is the function that is given to you. This is the function. Please try. Okay, so let's look at the solution. So u, which is equal to del phi by del x, is equal to y cube by 3 minus twice x plus x square y. Okay, that's it. V is equal to del phi by del y equal to x y square plus x cube by 3 plus twice y. Okay, so these are u and v. Now you need to check whether it satisfies continuity equation or not. So del u by del x will be what? Minus 2 plus twice xy. Del v by del y will be what? Twice xy plus 2. If you add these two, are you getting 0? No. If you add these two, you are getting 4xy. If all the computations are correct. Okay, you please check once. But if I hope that these computations are correct, then this is not equal to 0, and it hence it does not represents a possible, it does not represent a possible flow case. It does not represent a possible flow case. Okay, so is this problem clear, or do you have any doubt? Is it clear? Okay, since there is not much response, I am concluding that there is no doubt. And with this, let's stop for today. We'll again meet next week, that is on Saturday at 4 p.m. And we'll discuss with some further problems relevant to week 3 of this course on hydraulic engineering. So thank you very much. And of course, if you have any doubt, uh, not related to today's session, but in general, any doubt related to the course content or anything else, you can ask. Okay, if there is no doubt, then we'll stop here. The recordings will be made available to you, so you don't have to worry about the recordings. All the best. Thank you. So you can leave the meeting. Thank you very much. I am stopping my screen. Okay. Thank you.